So good afternoon, AP Stats kids. It's Monday the 27th. Hope everyone had a good weekend. Hope everyone is safe and healthy at home. We actually have 2 more weeks of this. So originally, we were going to end on May 1st, which is this Friday. And Luke and I had planned on this week being sort of prep for AP exam, review, those types of things. But the College Board decided to add another week, and that was based upon when the actual AP exams are. So this week, we're going to pretty much do, for all intents and purposes, review for this year's modified exam. Now, tomorrow, Luke had originally scheduled, which has been changed. So if you haven't seen all the changes on YouTube or AP Central, I just want to let you know sort of verbally. Tomorrow was originally going to be, know your calculator and, what buttons and which are the best features and functions to use. That's changed because the decision this year is to make the exam sort of calculator neutral, for lack of a better term. You can and should use your calculators. If you have one, that's great. If you don't have one, the exam's going to be written this year so that the calculator probably won't give you any advantage at all. So sort of calculator neutral. So then we decided, well, if the exam's going to be relatively calculator neutral this year, Luke's going to do another session on p-value, and is that currently the best method to make decisions in the real world? And so kind of an interesting little topic tomorrow, perhaps a little bit different. Then a week from today, and we're still sort of designing it as we move, so it's not 100% finalized, but a week from today, we're actually going to have you do two problems sort of in class. So on Monday, you'll do the 25-minute FRQ with Luke, and then on Tuesday, he'll walk through the answers with you. A week from Wednesday, you'll do the 15-minute FRQ with myself, and then Thursday, I will go through the answers with you. And then next Friday would be kind of the May 8th would be kind of the wrap up, and Luke and I want to kind of wish you all good luck and thanks for listening in, and some of the lessons we learned, some of the things we did well, and perhaps some of the things we didn't do as well. So stay tuned for that. That's coming next week. We actually want you to pretty much go through a mock exam, perhaps no different than you would do in your classrooms, if we were all back at school. And for most of us, I don't think that's going to happen. So anyways, welcome back. Hope everyone is safe and healthy. Give me a second here to get my PowerPoint, and we'll get rolling today. So again, welcome back. My name is Brendan Murphy, and I teach at John Baptist Memorial High School in Bangor, Maine. Very interesting school, great place to work, and I miss my kids. You probably miss your friends and your teachers. Luke Wilcox teaches at East Kentward High School in Michigan, and probably, hopefully, you've seen both of us. So hopefully hopefully we've helped. Here's the homework that Luke assigned on Friday. So based upon records kept at a gas station, the distributions of gallons of gas purchased by customers is skewed to the right with a mean of 10 gallons and a standard deviation of 4 gallons. So I think I would draw a quick sketch maybe down below, but again, this is a multiple choice, and this year's exam is going to be all free response, but Luke and I still feel that there's some real important concepts that we can address in a multiple choice, even though this year's exam will be all FRQs. And this year's exam is different, it's modified. I don't know exactly what's on the exam, nor does Luke. We know it will be different, and so perhaps there could be, parts A, B, C, D, E, F or something, and maybe 1 or 2 of them feels a little bit more like a multiple choice question. But again, total speculation on my part, so let's not go anywhere with that. So a random sample of 64 customer receipts was selected, and the sample mean number of gallons was recorded. So I'm taking a sample size of 64, so N is 64. That's pretty good sample size, and I can live with that. I'm pretty happy about that. Suppose the process of selecting a random sample of 64 receipts and recording the sample mean number of gallons was repeated for 100 samples. So I'm taking a random sample of 64, I'm finding the mean, and I'm doing that 100 different times. So I'm clearly not doing a full-blown sampling distribution. I don't know that for a fact because I don't know how big the population is. But I don't think I'm doing a full-blown sampling distribution here. But it feels like I'm starting the process of trying to do a sampling distribution. Which of the following is the best description of a dot plot created from the 100 sample means? So I'm just going to go to my document camera here. Okay, same problem. So I think it said what, skewed to the right, and so it may look something like that, I guess, I don't know. And we know the mean is 10. Well, if I take 100 samples of size 64, the central limit theorem says that the shape of my sampling distributions of the sample means will become more and more approximately normally distributed as my sample size gets larger and larger. So I'm feeling that the shape of my sampling distribution, or in this case, the dot plot, right? Same thing, will be approximately normally distributed. So I canceled out that one and that one and that one. So those three, I felt pretty confident that I could get rid of those relatively quickly. So the dot plot is approximately normal with 10 gallons and a standard deviation of 0.5 gallons. So I have to figure out that. I'm gonna have to figure out the standard deviation of the sampling distribution based upon my sample size or using my sample size. In E here, the dot plot is approximately normal with a mean of 10 gallons and a standard deviation of 0.4 gallons. So the difference here was, which one of those is correct? So I said the standard deviation of all my sample means would be 4, which was the standard deviation that I had started with, 4 gallons, over the square root of n, and n we said was 64. So I said 4 over 8, or 1/2. So I got the answer D here. And that's really a nice problem. And my students, I've given them something similar to this in the past. And I think what they always say to me is, Mr. Murphy, we have the 64 and we have the 100 here. And they don't know what's what. They don't know which one's the sample size and which one's how often do we repeat it and those types of things. So I really like this problem that Luke picked, and it hits upon a pretty important concept. So hopefully that helped. We'll get back to my PowerPoint here. And so the goal of today is to go through 2 free response questions. Hopefully I have enough time. And actually then grade some student papers. So I'm gonna, I guess, make you AP readers, not really, but talk about a little bit about the reading, what happens, how do we grade your papers, what goes into it, what happens if you do this. And the goal is Luke and I really wanted you to see how easy it is to perhaps lose a point or lose some points by imprecise wording, or perhaps on the flip side, sometimes how easy it is to get the point, or how easy it is to get context in there, something like that. So I'm going to do 2 free response questions. Then we'll look at some student samples. We'll grade those. We'll become AP readers, and hopefully you can get some benefit out of it. I like to do this with my students as we get closer and closer to the AP exam every year. A lot of AP teachers do the same thing. So again, here's some links to updated info. We've talked about it. So for the sake of time, we'll move on. So the AP reading, each year about 700 to 800 high school and college professors, get together in June to read, grade all of your AP exams. We've been reading in Kansas City for the last few years. This year is going to be a virtual reading. We're not going to Kansas City. Many of us are a little disappointed with that, although clearly the right decision by the College Board, but it's kind of a fun week. So the College Board likes to have a 50-50 split between high school and college professors. So at the reading, I have a partner all week. He and I, or she and I, will work together. And almost always my partner is a college professor because I'm a high school teacher. And we have a great week together. We work really hard, but we have some fun. And we're constantly talking back and forth about, how do we grade this? So we want to make sure that we're giving all students the points that they've earned. We can't give you points, you earn them. I like to tell my students. I can't mark it wrong or right until I fully understand 100%. And at times I'm confused and I talk to my partner and vice versa. So very collaborative week. This is some of the best professional development that high school teachers can go to. And many of us enjoy this week year after year after year. I have what I call my reading friends. I might see them literally once a year at the reading, and we have a lot of fun. So maybe your teachers are readers. If so, great. Have them look up Luke and I. If not, maybe mention to your teachers, hey, Mr. Murphy said the reading's a ton of fun. Maybe you can become a reader. We're always looking for new readers. We work hard all day, but there are plenty of fun things to do at night. And it's one of the best weeks of the year for many of us. We really enjoy it. My wife thinks it's a little weird, and my students definitely thinks it's weird that I want to go grade papers for a week. And that doesn't sound fun at all, but it really is. We have a good time. We work really hard. So this year's reading will be virtual. We'll be reading at home this year. Maybe one of your teachers is a reader, and Luke and I have worked with them in the past. Who knows? So there's what we call a pre-reading phase, and the leadership team actually is just randomly sampling. You guys would understand that. Student papers, and we're basically trying to see how our scoring guidelines are working. So we've come up with the problems, and the test development committee has come up with scoring guidelines. And we don't really know how they're going to work until we start grading student papers. So we actually start randomly sampling papers, and we want to see how well the scoring guidelines are working. There's many good discussions back and forth, debates. At times we need to make tweaks to the scoring guidelines, or as we like to say, the what if game. What if a student wrote this? Would this be enough to earn full credit? Or what if a student did this? How are we going to handle this? So the pre-reading is designed to see how well the scoring guidelines are working. The readers show up usually on day 4 or 5, and the readers get trained for 3 to 4 hours before they actually read any student papers. So it's a very intensive, long, very detailed training before we actually sit down, grab a student's paper, read it, and come up with a score. So good training could be 3 to 4 hours. I talked about partners. Readers are encouraged to work with their partners all week. Usually high school teachers get paired with college professors. We ask each other's questions. We resolve issues, discuss the scoring guidelines. Readers must follow the scoring guidelines. So it's not how I would grade it in my classroom. It's not what I would want to do. It's I follow that scoring guidelines. And my job as a reader is to make sure that I'm scoring consistently from day 1 all the way to day 7. Very complicated process. I'm just giving you the tip of the iceberg, but it works. And it's really cool to see it all come together on day 7. Each grading room has 2 what we call table leaders. These table leaders act as kind of quality control. They make sure that the readers are following the scoring guidelines. Table leaders also answer questions from readers on student responses that are perhaps a bit harder to score. No matter what we do in that 3 to 4 hour training, we're going to run up on student papers that are just we haven't thought of, or we hadn't seen anything, and how do we handle it? So very collaborative process for the whole week. And there are times where we might spend 10 minutes on one student paper for 1 point. I mean, we really will spend the time needed to make sure that you're getting all the points that you've earned. And today, I think you'll see how easy it is sometimes to get those points, and perhaps sometimes how easy it is to lose those points. So I've found 2 free response questions that I've used in the past, and there's some good student sort of samples that we'll practice. So this was from the 2005 exam. Some boxes of a certain brand of cereal include a voucher for a free video rental inside the box. Get a little toy down the bottom. The company that makes the cereal claims that a voucher can be found in 20% of the boxes. So when I see the word claim, I think I know I'm leaning maybe towards a hypothesis test, but let's keep reading. However, based on their experience eating this cereal at home, a group of students believes that the proportion of boxes with vouchers is less than 20%. Right now, I know it's a one-sided test. We don't do one-sided confidence intervals, so it's probably a hypothesis test, but let's keep reading. And then I'll ask my 4 questions like I always do. This group of students purchased 65 boxes of the cereal to investigate the company's claim. So that's my sample size. Students found a total of 11 vouchers for free video rentals inside or in the 65 boxes. So P hat's going to be 11 over 65. Suppose it is reasonable to assume that the 65 boxes purchased by the students are a random sample of all boxes. I always like that random of this cereal. Based on this sample, is there support for the students' belief that the proportion of boxes with vouchers is less than 20%? Provide statistical evidence to support your answer. So hopefully by now you're seeing that, this can't be a yes, no, this has to be a full-blown inference problem. And I'm going to walk through all of the different steps real quick, and then we're going to be, I'm going to ask you to become AP readers. So I asked my 4 questions. Does this feel like a hypothesis test or a confidence interval? I was pretty confident, no pun intended, that it was a hypothesis test. Do we have 1 or 2 samples? Well, we have 1 sample. Are we dealing with means or proportions? We're dealing with proportions. And so I would read a Z table or a T table based upon that. So I've labeled this test a 1 sample hypothesis test with proportions. There's plenty of other ways you can identify this test, but that's the language that I've used with my students, and it seems to make sense. If I do that, then when I get down to the math mechanics part, I do not need to write the formulas. I think when we do the student papers, you're actually going to see that all of them or most of them do that, but you don't have to. So I'm going to do my null hypothesis first. That would logically be my first step. You'll see when we grade student papers that that's not always what students do, and that's okay. So I said my null hypothesis, P is equal to 0.2. My alternative is P is less than 0.2, and I got that from the wording up here. I always want to identify the parameter, so I said P equals the proportion of all boxes of this brand of cereal that contain a voucher. When we go to the student papers, that year this was not needed, but I'm going to say keep doing it, and I think rubrics have changed over the years, and I'm going to say that please keep doing that. This year in 2005, students didn't have to have that, but I'm going to say stick my neck out a little bit and say we want you to do that moving forward. So I need to check my conditions and assumptions. So over here, I said P hat was 11 over 65 or 0.169. Well, that is a little bit less than the 0.2 that the manufacturer claims. Is that enough? And I just don't know. I need to run the test. So the data was randomly selected as stated in the stem of the problem. So that's always good. That randomness there is nice. I want to make sure that the population is greater than 10 times my sample size. So is the population greater than 10 times 65? The population of cereal boxes greater than 650. I guess that's an assumption. I have no way of proving that. I don't know by reading this problem. So I said, the population is probably greater than 650 cereal boxes. That's a reasonable assumption. How many boxes of cereal does General Mills make in a day? I have no idea, but it's probably more than 650. NP greater than 10 and N1 minus P or NQ, depending upon how your book does it. So I said 65 times 0.2 is 13, and that's greater than 10. Down here, I said 65 times 0.8 is 52. Both of those greater than 10. We need to see that math. We need you to see that you plugged in those numbers. You just can't put a check and say greater than 10. So it feels like we're okay with the conditions and assumptions. Since I named the test up here, I don't need this formula down here, but I figured I would do it anyways. So I just said my Z is equal to my sample statistic minus my population parameter over my standard error. Did some quick math and I said my Z-score is negative 0.62. I went to the calculator and said, what's the probability that Z is less than minus 0.62? So I get a p-value of 0.2676. That's pretty big, and so I don't think the evidence is strong enough. So my conclusion, again, my first, if you sat through any of my sessions when I was doing inference, my first sentence is maybe a little generic-y, but since our p-value of 0.2676 is greater than our assumed significance level alpha is 0.05, we failed to reject the null hypothesis. That's every time I do a hypothesis, that's basically my first sentence. Notice I have no context in there. So my second sentence tries to get that in there. So the data does not provide convincing evidence to support the student's belief that the proportion of cereal boxes with vouchers is less than 20%. I haven't proved anything. It's not an experiment. The evidence doesn't lead me to believe that the evidence isn't strong enough for me to refute the manufacturer's claim. So now let's look at some student papers. And before we do that, here's the official College Board scoring rubric. For the sake of time, I won't walk through everything here, but this is sort of what a reader is going to be looking at, that in much more detail. But That's pretty much what we're going to look at. This is how we're going to grade your papers. And again, I need to follow the scoring guidelines, not do what I want to do. I think Luke, I watched him the other day a little bit. He talked about typically we grade things, each part of a problem we grade EPI, essentially correct. Doesn't have to be perfect, partially correct, incomplete or incorrect here. And so for each of those 4 components, we're going to walk through a student's paper and give them an EPI. EP or I, sorry. So, the first thing I look for is sort of the name of the test. So the student here says, I will do a proportion z-test. Okay, different how I would say it, but nothing wrong with that. I'm okay with that. Up here, that looks like p hat, and then the student actually looks like they're doing the standard error or something here, and spec 0.2. I don't, specification maybe. I don't know exactly what that is. Looks like they're doing the assumptions first, which is not wrong. I wouldn't do it that way, but that's okay. But down here, there's a box. And so the student does say HOP is 0.2, HAP is less than 0.2. That year, we did not ask students to define the parameter. So I'm going to give the student an E for that first component. Have they correctly done the null and alternative hypothesis? So students earned an E. Generally, an E is worth a point, P is worth half a point, and I is worth no points. Oversimplifying again, but generally that's sort of the rule. But we won't get into all the little nuances of the reading here for the sake of time. I'll go up and look at the student's conditions. Assume the sample of boxes an unbiased estimator of the true proportion. Assume that the population is greater than 10n. Population, yes, that's okay. That's good. Here's my NP check. Here's my N1 minus P check. Student plugs in the numbers. That's good. Student has not talked about it being randomly selected. The old rule way back when was if it was in the problem, not to repeat it. Let's follow the new rules. The new rules, we would want to see the student do that. But in this year, in 2005, this student met all those requirements. So I'm going to give him a second E for those assumptions and conditions. Again, I really want to see that random, and please put that. It looks like a student's drawn a normal curve, way better than my normal curve, so good for the student. Z test stat equals stat minus statistic minus parameter over standard error. Not needed because the student named the test, but it's not wrong. I see where the student plugs in the numbers. I see the student got the same z-score, minus 0.6210 that I got, so that's good. What's the probability that p hat is less than 0.1692? Is the probability that z is less than minus 0.620? Student is actually giving me sort of the calculator speak. That's not really needed, but it's not really wrong. And the student's done a really good job of telling me where they're getting all those numbers. The student basically got the same p-value that I did. So we're good there. So for that third piece, what I call math mechanics, I'll give the student an E. And then down here, I'm hoping this is kind of their conclusion, in context, what decision are they going to make? Assuming the proportion of vouchers found in boxes is 0.2, there is a 0.2673 chance of getting a sample with a proportion more extreme than 0.1692. Okay, I different than how I phrase it, but I can live with that. Again, that 0.1692 was just my p hat. Large P failed to reject the null. Again, I probably would have tied that into, my alpha is 0.05, but that's a pretty high p-value, pretty large p-value. We're not going to reject very often at a p-value that big. There is insufficient evidence to claim that the proportion of boxes with vouchers, I actually always put a U there, and at first I said vouchers, but vouchers, that's fine. I'm pretty messy, so I'm not going to worry about this student's rating. That the proportion of boxes with vouchers is less than 20%. That's a pretty good conclusion, different than mine, clearly different than mine. This student earned an E. The readers will get pretty good with that after a couple days. That student earned 4 out of 4 points. Is it perfect? No. Is it pretty good? Yes, it's a very good paper. Having read thousands, the student really understands it. I think has done a pretty good job. Very clear, easy to read. I'm good with that student. So that student earned 4 out of 4 that year. Okay, here's the next student. If I say, the student should have done this or that, I am not making fun of these students, please. That's not the intent. These students work really hard. You work really hard. So this is just an educational exercise. I'm not making fun of these students. I should have said that earlier. So hopefully that was clear. This student is circling lots of good things up here. I actually tell my students to do the same thing, so that's good. One proportion test, that's weaker. I don't love it, but it's okay, and I think I know where the student is going to go with it. If the student correctly names the test, they do not have to write the formula. Well, this student does a pretty good job with the formula there, so that was good. I was not 100% comfortable with this. Maybe a nice recovery here. So HO and HA, student has it. So that's an E. Again, really simple. If that was down here in the bottom of the paper, I still have to read it. So it doesn't matter where it is in your paper. The readers have to read your whole paper. Look in if there's something written up here, down the side, I have to read it. I cannot, until I fully understand what the student's trying to say, I can't either give you points or take points away. How's that? So student does a great job here. We'll give them the E for that. Let's look at their assumptions. Student says it's a random sample. Okay, that's good. Population is sufficiently large. Again, years ago, we were maybe not as strict as we are today. I think today we would have wanted to see, population is greater than 10n with numbers plugged in. But the student is saying it's probably way more than 650 serial boxes, and so we're pretty good there. Here's my NP, NQ checks, or NP, N1 minus P checks. Student plugs in the numbers, both greater than 10. Student earned an E that year for the assumptions and conditions. Pretty good job here. Again, I would have liked to see this. I think today we would want students to do that and plug in the numbers, but this was 15 years ago, and rubrics change over time. So up here, it looks like student is just doing P hat, does the math for me. Here's the math mechanics. There's your formula. Student plugs in the numbers, comes up with a Z-score, minus 0.6202. That's the same one I got. Circles the p-value, didn't copy very well, gets the same p-value, 0.2676 that I got. I'll give him an E. Student's doing great. E, parts A, B, and C. Therefore, we failed to reject the null hypothesis. Okay, I agree with that. The proportion of boxes with vouchers is equal to 0.2. That I don't like. We can't make that definitive of a statement. I haven't proved anything. This isn't an experiment. There's no causation. The evidence is not strong enough for me to reject the null, but I definitely can't say that the null is true. So the student actually gets an I here. I can fix this with 1 or 2 words. This is just too definitive, too strong for us. The proportion of boxes with vouchers is definitely equal to 0.2. I added the definitely there for to make it a little bit stronger, but that student understands the problem. They've done a great job here, here, and here, and literally they're 1 or 2 words away from getting an E here. And so this student only got 3 out of 4 points that year. And I, there are times we feel bad for the students when we're grading. 1 or 2 words, if they had changed, they probably could have gotten another point or 2, but we just felt that was just too strong. That's really not what's happening in a hypothesis test. I can't say that the null is definitely exactly equal to whatever. So third student here, again, hopefully you guys are getting the hang of this being a reader. You can tell your teachers now you're an approved AP reader. Only kidding. Okay, here's the name of the test. Use a 1 proportion Z test. Okay, that's good. Yep, the student names the test correctly. Therefore, they don't need this formula. Although again, that student has done a really good job with the formula. Here's my null and alternative. P is equal to 0.2, P is less than 0.2. Okay, I'll give them an E for that. That should be an easy E. This year it was an easy point, we hope. Again, students did not have to define the parameter that year, but moving forward, please do that. So it looks like this is their assumptions and conditions. Sample size is N is 65. Okay, that's a true statement, but I'm not sure that's a condition. P hat is 11 over 65 or 0.1692. Again, these are both true statements, but they're really not the conditions. Boxes are an SRS, so that was good. That was given to us. But notice the student doesn't have your, what I call, your NP and NQ checks. Population is greater than 10 times the sample. So student got an I here. It's just not, they really didn't do a very good job with the assumptions and conditions. Again, I'm not picking on the student here. They thought they did, but they really didn't. So they didn't get that point there, unfortunately. Let's go down to the math. So the student has the z-score formula, plugs in, looks like the numbers are all in the right place. Z is equal to minus 0.6202. Yep, we've seen that number before. My p-value of z is 0.2676. Yep, that's all good. I'll give the student an E. So the student has an EIE. So far, so good, except for the assumptions. So I guess this is going to be my conclusion. What are we going to do with all this information? So C is 0.95 default, alpha is 0.05. I guess confidence level is 0.95. Again, I wouldn't write it this way, but I'm okay with it as a reader. Our p-value of 0.2676, excuse me, greater than 0.05. That's a true statement, except the null. Well, boy, unfortunately, that word right there is really bad in statistics. We don't accept the null. I don't like to accept the alternative. I either reject the null in favor of the alternative or fail to reject the null. So yeah, student loses it really based upon that one word. There's not enough evidence to reject the null. Again, there's no context here. There's no cereal boxes, there's no vouchers, anything like that. So unfortunately, this student got an EIEI, 2 points. And unfortunately, I on some level really think that the student sort of understands the problem, has actually made the sort of the correct mathematical, what we call linkage here. But this word here is just not a good statistics word, and there's no context. And so the student earned 2 points out of 4. And do you see how easy it is to have a wrong word, and that's enough to cost you a point or two. So we feel bad for the students, but we got a lot of students to read our grades, so we keep moving on. How's that? So I think I did this problem the other day with probability. I'm 99% sure, confident, no pun intended, that I did this one. So I'll go through the answers real quick because I want to make sure we have enough time for the student responses. So a shopping mall has 3 automated teller machines, ATMs. Because the machines receive heavy use, they sometimes stop working and need to be repaired. Okay, that makes sense. We're just setting the stage here. Let the random variable capital X represent the number of ATMs that are working when the mall opens on a randomly selected day. So we talked about random variables. I think that was last Wednesday. So I did this problem on Wednesday. The table shows the probability distribution of X. That's your random variable. So it looks like we either have 0, 1, 2, or 3 ATMs working. 0 would be a bummer, right? You go to the mall and there's just no ATMs working. You need to get some money. Here's the associated probabilities with each one of those sort of outcomes or ATM machines working. I'm going to add those up, and they do equal 1. So that's good. That's one of the requirements of a random variable, right? So what is the probability that at least one ATM is working when the mall opens? So again, many times I just repeat the question, and I'm guaranteed to get context in if I can do that. The probability that at least one ATM is working when the mall opens is 0.21 plus 0.40 plus 0.25, 0.85. Okay, keep that number in mind and keep this sort of context in mind. Part B, what is the expected value of the number of ATMs that are working when the mall opens? Again, I'm just going to repeat the sentence. The expected value of the number of ATMs that are working when the mall opens. And I like to say, outcome times probability. plus outcome times probability, plus outcome times probability, plus outcome times probability. That's going to give me my expected value. I did that math and I got 1.73 ATMs. I do not want to round that. I want to leave that number alone. Unless specifically told to round, we want to leave that there. So that's a mean or average, and we just don't want to round that. And I have graded papers where students might have rounded different problem and they lost points for that. So leave that alone, don't round. Let's keep moving forward. I think we've earned some points. What is the probability that all three ATMs are working? So all three ATMs are working. Given that, well, that sounds like a conditional probability, right? Given that at least one ATM is working. So I said the probability that all three ATMs are working when the mall opens, given that at least one ATM is working. Well, all three are working is the 0.24. All three working is 0.24. Then I added up at least one working, so I didn't need to worry about zero. So I added up those three probabilities. I got 0.24 over 0.85, 0.282. Again, going fast because I want to make sure that we actually look at the student papers, and I think we'll be okay. Given that at least one ATM is working when the mall opens, would the expected value of the number of ATMs that are working be less than, equal to, or greater than the expected value in part E? Explain. Well, the expected value in part B was 1.73. Given that at least one ATM is working, well, I guess I'm going to worry about zero. I'm not going to worry about zero ATMs. I'm told that either 1, 2, or 3 are working. Well, if this was sort of my, I guess, my revised random variable, those three probabilities would have to add up to 1. And so each one, my gut says, would be proportionately higher. And so it feels like the expected value will be larger. Why? Because I'm taking the 4 events and really just using 3 of them. Those 3 probabilities need to add up to 1. So each one would be proportionally larger or bigger. When I multiply, it feels like it would be greater. So the expected value would be greater than the expected value in part B. Again, I just wrote that down. Since the probability for 1, 2, 3 ATMs would be proportionately, maybe larger or something would be a better word than increase. Okay, so we did that the other day. 4 parts. Again, we're gonna grade each one of these either EPIs, essentially correct, partially correct, or incorrect. So let's look at student 1. Again, student makes a mistake here. I'm by no means making fun of these students. My students, I wish were all perfect. They're not. I wish Mr. Murphy were perfect, and he's far from that. So the probability that at least 1 equals 1 minus the probability of no ATMs, 1 minus 0.15, 0.85. Well, that's different. That's actually kind of a cool way of doing it. Perhaps maybe a little bit easier than me. Correct number. I see some math there. Give the student an E. I'm happy with what they've done. What is the expected value? What is the expected value of the number of ATMs that are working when the mall opens? EX, expected value of random variable X. Student does the right math, 1.730 ATMs. I've seen the work. Perfect world, I'd love maybe some words, but it's there. I'm going to give that student an E. Again, E doesn't mean perfect, and 4 out of 4 doesn't mean perfect. What is the probability that all 3 ATMs are working when the mall opens, given that at least 1 ATM is working? Student does a very good job here of sort of the conditional probability in words. Has the correct numbers, 0.24 over 0.85, 0.282. Excellent job right there. Very, very, very nice answer. Clean, easy, perhaps better than mine. Down here, student needs to talk about less than, equal to, greater than. The expected value for the number of working ATMs would be greater than that in part B. Okay, so that's good. The student has the right answer. Because at least 1 ATM must be working, there is no longer the X value in the probability distribution. So I think the student is saying, you know, we're getting rid of that 0. Thus, in this distribution, the probabilities of having 1, 2, 3 ATMs all go up. Okay, that's sort of what I talked about. That's good. When finding the expected value by doing EX equals X times probability of X student actually gives me the formula, because all the probabilities values increase, the sum increases, and EX is greater. That's really nice. Yeah, the student probably didn't need all of that, probably didn't need the formula, but E, that student got 4 out of 4. Very, very nice paper there. Yep, very nice paper. Okay, next student. Student adds the 3 probabilities, 0.85. I'm going to give him the E, it's there. The problem says, what is the probability? The student gave me the probability. I can follow their math. I can see where they got that number. I wish there was some more words or a sentence, but it's there. So I'm going to give him the E. That's what the scoring rubric said, scoring guidelines. What is the expected value? Expected value, student does all the math, gets the same number, doesn't round. Give him an E here. What is the probability that all 3 ATMs are working? Student has the right numbers. I wish they had over here maybe the formula or some words. 0.282. Student gets it. Give him an E. Little bit of a minimalist here. Maybe some more words would be nice, but it's there. It's marginal. I think you could see that the first student was a little bit stronger from a communication point of view, but this student's doing okay. Student's doing okay. Part D, student says it would be equal to, well, we said greater than, so I don't think this is going to be right here, but I need to read it. Equal to, because expected value is calculated by, gives me the formula. And I think the student was confused that since 0 times any number is 0, that it wouldn't change. And so that's actually an incorrect answer. So the student got an EEEI. Student earned 3 out of 4, which is still a very good score. There's absolutely nothing wrong with that. And that was kind of a common mistake that year. I think students said, oh, well, if that's 0, 0 times any number is 0, so that number won't change. They didn't see that these probabilities would proportionally increase. So that student earned 3 out of 4. Okay, here's the last student, I think. And in part A, we see no math. We see a number. We call that a bald answer. My students get a kick out of that every time I say bald answer. They ask me if it was named after me, and I say, no, that wasn't named after Mr. Murphy. I don't like that. I mean, I know where they got the numbers from, right? It's the right answer. Student doesn't give us any words, doesn't give us any context, doesn't show me where that number comes from. That student earned a P. Think of P as a half point. It's not quite that simple. E is 1 point. Again, not quite that simple, but do you see how easy it is to lose, to go from an E to a P? If the student had just added those 3 numbers and put it down here, that student would have gone from a P to an E. So please, please, please show us your work in context. Use the calculator to check your math, but always show us your math. How's that? I think Luke says it like that. What is the expected value? Really hard to read the numbers here, but the student does have expected value 1.73. Here they show me the math, so I'm going to give that student an E. That's what the scoring guidelines say. I'm good with that. Student showed me the math. Part C, what is the probability? P of A given B, again, I wish it was more contextual, but 0.24 over 0.285. These are the right numbers. That's actually the wrong number there. I think I got 0.282. So it was weaker here, A and B. I don't really know what A and B is. Student has the right numbers here. That's good. The wrong math there. Student earned a P there. And again, if that number were correct, 0.282, the student probably would have gotten an E here. That's weaker. I'm not thrilled with it, but it's okay. If the student had shown where those 3, added those 3 numbers, they probably would have gotten an E here. And the student may have gotten an extra point on this problem. How's that? So hopefully this is helping you, exactly what are the readers looking for, show us your math in context, all of that good stuff. Part D, the expected value would be equal to, well, that's the same mistake that the previous student made. because the probability of 0 working when the mall opens does not affect the expected value, et cetera, et cetera, et cetera. I would read it, but for the sake of time, I won't. Student got an I there. That was very common that year. Students said, oh, well, it's going to be the same. 0 times anything is 0, so the numbers won't change. So this student got a P, E, P, I, 2 points. And we like to say, you know, they left some valuable points on the table there. If the student had only showed us the math here, you know, added those 3 numbers, maybe checked it on the calculator, this student very easily could have gotten a 3 out of 4. So let's kind of wind down for the day here. Hopefully that was an exercise that you found helpful. So we did the cereal boxes, right? We did that one. So hopefully now you're feeling a little bit more comfortable with the scoring guidelines, the rubrics, how they're developed and how readers are trained to read your free response questions. It's really quite a logistical exercise to get 700 to 800 people in a room. Last year, I think it was around 250,000 students. So 250,000 times 6, 1.5 million, if my math is correct, answers. We have to grade all those in a week. And we want to finish on day 7 right around the same time. So it's unbelievable logistical problem, fun to solve. Extensive training, we need to follow the scoring guidelines, not do what we think. Okay, so we're trained to follow those scoring guidelines, and the training is very extensive and very detailed. All week long, I'm working with my partner. My partner is typically college. If we have questions, we go find a table leader. We can go up to question leader. There's sort of a hierarchy of different positions when we run into problems. Again, similar to all problems in AP statistics, you should be able to write your answer in a clear, concise solution and context. And hopefully you saw that literally on some student papers and how they left, as we like to say, some valuable points on the table. How's that? Here's your homework for tonight. Luke will take over tomorrow. Now again, Luke's is going to be a little different tomorrow. Talking about p-value and statistics, and is that the right sort of way we should be, right process for hypothesis testing. So I'll leave that up to him. Hopefully he likes the problem that I picked. So I just wanted, there's I think 8 or 9 slides here, and we won't go through all of them. But some students have sort of said to the College Board, we want more practice. You know, Brendan and Luke are doing lots and lots of questions, but we want to sit down and do some of our own. So these next few slides sort of talk about how you can go on to AP Classroom and find some additional FRQs, free response questions to do, how you can check your answers, all of those things. So I won't walk through each slide here. But it's there if you want to go back and look at my, my little talk today and walk through some. By all means, practice makes perfect. My students are doing lots and lots of free response these last few weeks, and hopefully watching me on some of these as well. So thanks for watching. Hopefully you'll keep watching. Tomorrow is Luke. I'll be back on Wednesday. And Friday, so I'm doing Monday, Wednesday, Friday this week. Luke is doing Tuesday, Thursday. Again, this week is predominantly, tips for the AP exam. How to do well, how to write good responses, how to use your formula sheets, those types of things. Common errors, you saw that today. Some common mistakes that we see over and over again, and how you can really 1 or 2 words can sometimes cost you a point on a problem, and we don't want that to happen. Again, next week wasn't originally part of the plan, but the plan has changed, which is great. So next week, Luke and I will be same thing every day at 2 o'clock. Monday, we're going to give you the 25-minute FRQ to do. We actually want you to work on it during our live session from 2 to 2:45, or if you're watching it through tape, whenever, but we want you to sit down and literally walk through the problem. Tuesday, Luke will go through the answers. Wednesday, I'll do the 15-minute FRQ. Thursday, I'll do the answers. And then Friday the 8th, we're going to kind of have, sort of the graduation ceremony, whatever. We'll have a little, Luke and I will both be there that day, and we'll talk about, wishing you good luck, and hopefully we helped in those types of things. So hope we helped today a little bit. And you understand a little bit more about what happens at the reading and how we actually go through student papers and determine, how many points a student earns. So be safe, take care of yourself. Hopefully you can tune in tomorrow, and later on this week, I'll see you. So have a good afternoon, and we'll see you tomorrow. Thanks.